Well, thank you for, okay. Yeah, right. I was supposed to let you know about the recording.
Yeah, great.
Thank you all for being here today. It's my pleasure to introduce Tim Cronin. So he is currently a professor at the Department of at MIT, which has a program in atmosphere. You guys still have the PAOC, right? A program in atmosphere, ocean, and climate, which Tim is a part of. He started at MIT as a faculty member in 2017. So he's been there only a couple years. He did his undergrad actually at MIT as well.
Grad studies at MIT.
What's that?
I did my PhD at MIT, but not my undergrad.
Oh, I'm sorry, not your undergrad. Sorry, I meant graduate work. He did his PhD at MIT. Actually, he started there just after I left in 2009, and he switched to climate and atmospheric dynamics, I guess, from doing ecosystem modeling for a couple years at Woods Hole. So he saw the light and came around to the physical system. And no, that's not very nice of me. But he, after 5 years at MIT, he did a joint NOAA and Harvard postdoctoral fellowship, working with L.A. Zipperman on the process of cold air formation. And Tim generally works on kind of convection, radiation, and clouds, and combines theory and idealized numerical modeling experiments to understand the stability of Earth's climate and explore possible climates of other worlds. So it's my pleasure to introduce Tim Cronin. And here you go, Tim.
All right. Thanks a lot for the introduction and the invitation, Larissa. So I'm going to talk today about some very idealized numerical modeling of work I've been doing over the past few years, simulating rotating atmospheric convection under a range of dry to moist conditions. I should also say that people should feel free to interject with if they have questions. I know that the kind of Zoom talks slides going by you endlessly can get very dull, or if you miss something, it can be hard to catch back up as you would in a normal chat. And I'll try to be mindful of if there's a chat tab. If someone wants to chat me, I'll try to, if that lights up, can someone chat me just to see what that looks like? Okay, great. Thanks, Liz. So I'll be responsive to any questions that you pump into the chat too. Just if you want me to stop and say something again, or if my audio cut out and I don't know it, please let me know. So on Earth, in the current climate, the combination of planetary rotation and moist convection leads to the dramatic phenomenon of hurricanes or tropical cyclones. And hurricanes as a phenomenon in Earth's present climate are inextricably tied to water. So how we portray them obviously does them that justice. So the way we show hurricanes is vividly connected to how they mobilize, or how they've mobilized atmospheric water into a thick swirling cloud pattern, or by how they've moved ocean or rainwaters near the surface, kind of thrashing palm trees, or how they've dumped water on the surface through precipitation, leading to freshwater flooding or storm surge. And most of the damage from hurricanes comes not from their just strong motion of dry air, but from how they've moved water around, from their storm surge, from their freshwater flooding. But the basic question we want to dig into in this work is this: is moisture truly fundamental to the vortex dynamics of a hurricane? This might sound like nonsense given the previous slide. How can you imagine a hurricane kind of divorced from an ocean surface entirely, without dark clouds or torrential rain, and just underneath, maybe clear skies or dust or something? But the answer, the first stab at this question, based on one study from 8 years ago, is that no, you don't need moisture for a hurricane. I guess this is 9 years ago at this point. They found that you could get a dry storm readily in an axisymmetric atmospheric model, So this is looking in radius and height at both the dry model and a moist on the left and a moist model on the right. And that you could get a dry storm very readily in a dry axisymmetric model, sustained by strong surface sensible heat fluxes in the eyewall of the hurricane, rather than from latent heat fluxes as in the moist model. And so this was a nice figure from work by Mrowiec and Olivier Pauly and Steve Gardner. And you can see the tangential winds on the top panels compared in the two cases. You have this low level, strongly increasing winds with radius and then gradual fall off in both the dry and the moist cases, decreasing winds, tangential winds with height, and a deeper layer of radial inflow and outflow, but confined a little bit shallower in the dry case as compared to the moist case. Can people see my mouse, by the way? Is that coming through? I guess I can check. I don't see it. Okay, is there a pointer option? Okay. Is there, let's see. Okay. Well, we'll see how that goes. As Carrie Emanuel put it, a few years ago, this paper has been met in the literature with deafening silence. But I think it's fascinating, and it brings up a lot of questions for which we have few answers. So here are just a few of them. Are these dry storms even stable in 3 dimensions? What controls their intensity, size, and structure? What does the transition from moist to dry dynamics look like? So a little work has been done to address these questions, and I'm going to talk about some work that I've done over the past few years looking at these subjects. So a very legitimate question you might ask is, if dry hurricanes don't exist on Earth, why should we care about them? And my most compelling answer to that lies in the simplicity and the use of model hierarchy, or a set of models of varying complexity to better understand the real climate. So a lot of our understanding of how the atmospheric general circulation works stems from models that don't include the effects of moisture. And it would be great if we could, the way that like baroclinic eddies and mid-latitude dynamics, jets, storm tracks work, we understand a lot of that through dry dynamics. It would be great if we could further develop our understanding of hurricanes in a similar way, if the key ingredients are really just rotation and dry convection. It's not obvious that that's true. The possibility of rotating dry convection organizing into large-scale vortices also suggests that you could possibly conduct tank experiments or direct numerical simulation that might be able to produce these vortices over part of parameter space. And I find that idea really, really fascinating, and have a grad student currently working on that in the direct numerical simulation angle of things. So if we get back on campus at some point, we'll try some tank experiments. Related to that is the point that if dry rotating convection is all that's needed to produce a hurricane, then it might be possible to find hurricanes in simulations of just rotating Rayleigh-Benard convection, which would be a fantastic link to a huge body of work in applied math, physics, and engineering on convection. And finally, vortices like dry hurricanes might exist on other worlds or in deep past climates on Earth, even if they don't exist in Earth's present climate. So we're studying a phenomenon that's potentially quite general to rotating turbulent convection over a surface of large heat capacity. So the work that I'll talk about today is looking primarily at 2 ways of exploring the moist to dry transition of turbulent rotating atmospheric convection confined into miniature doubly periodic worlds. So we've used primarily 2 ways of drying out the surface. The first is just to reduce the surface moisture availability while holding the temperatures fixed. And the second is to make the surface cold, which has the effect of reducing the surface saturation vapor pressure and shifts the surface energy balance towards sensible heat fluxes and away from latent heat fluxes. And then I'll go into a little bit of exploring another dimension of parameter space, the rotation rate, towards the end if there's time. And the punchline, what I hope you remember out of this talk, is largely summarized in this figure in the title of the slide. So dry hurricanes readily and rapidly form in rotating radiative-convective equilibrium. Second, dry storms are less intense than their moist counterparts and have smaller outer radii relative to their bigger eyes or regions of maximum winds than moist storms do. And third, but a bit more nuanced, is that the dry transition from dry hurricanes to moist ones, or vice versa, appears to be discontinuous for storm genesis, but continuous and smooth for established storms and in most properties. So this is interesting in part and because there's a lot about tropical cyclogenesis that we don't understand, and being able to kind of switch off spontaneous cyclogenesis by going into a certain range of parameter space where otherwise things are similar to 2n members is kind of neat. So this talk will have three main parts. First, I'm going to give some background about tropical cyclones and how to make them in numerical models. Then I'll move on to some of the work that I've done, first talking about simulations of dry hurricanes and the moist to dry transition, and then discussing the sensitivity to rotation rate if there's time. So the essence of a hurricane or tropical cyclone, I'll use those terms interchangeably through this talk, it lies in its energy source, which is convection driven by a supply of moisture and or heat from the surface. So tropical cyclones are fundamentally different from extratropical cyclones because they draw their energy from the surface. They like symmetry and a lack of wind shear. They're inherently diabatic phenomena that require air to cross isentropes as it circulates through the storm. Whereas extratropical cyclones, on the other hand, draw their energy from large-scale horizontal temperature contrasts. They're inherently asymmetric, and they form most readily in environments with strong shear. And the flow in them can be largely viewed as an adiabatic exchange of cold air moving downwards and equatorwards, and warm air moving upwards and polewards. So hurricanes in the present climate are largely confined to the tropics, because only in the tropics do we see these combined ingredients of weak horizontal temperature gradients, relatedly weak vertical wind shear, and also large disequilibrium between surface and nearest air that allow for strong swirling winds to pull more heat out of the surface and strengthen an incipient vortex. Hurricanes also require some amount of planetary rotation to project onto the local vertical direction, and that's seen from the gap in tropical cyclones right around the equator. There are some rare exceptions to hurricanes being a tropical phenomena. So there are sometimes cyclones like hurricanes found in the Mediterranean or over the polar seas in the North Atlantic, which are relatively warm compared to the overlying air in winter. But for the most part, hurricanes are a tropical phenomenon in the current climate. So I talked briefly about the idea that hurricanes are fundamentally diabatic, requiring heat throughput to operate, and this works best in the current tropics. I want to go into this a little bit more. So the diabatic essence of tropical cyclones mean that they can theoretically reach a steady state where the overturning circulation in radius versus height space looks like this. It looks like a heat engine. It looks like a cycle if you go from point A, inflowing along radius, to point B, outflowing and ascending through the eyewall convection to point C, and then slowly returning through radiation and subsidence back down to point A. In the other two panels shown here of pressure volume or moist entropy temperature space, these are both showing cartoons of the overturning circulation in thermodynamic coordinates. So in pressure volume space, as you go from point A, which has relatively high pressure and low volume, or basically a relatively dense air at a given pressure, and you expand nearly isothermally in the inflow leg going from point A to point B, then you ascend moist isentropically to point C, decreasing the pressure a lot and also increasing the volume occupied by air, and then you go back to point A. This cycle encloses a positive area and thus is capable of doing work on the environment. And so the idea that this thermodynamic cycle encountered by of how air flows through a tropical cyclone enables us to think about it in the heat engine perspective, where the possible work done per unit air that traverses through this cycle can be balanced in steady state by frictional dissipation of surface winds. And this is also shown in the third panel on the right by the same plot in temperature moist entropy space, where the cycle becomes relatively simpler and just turns a triangle. So the idealization of the inflow leg of the secondary circulation is that the air increases in moist entropy at nearly constant temperature, so it just goes horizontally to point B. It decreases in temperature by ascending through the atmosphere at nearly constant moist entropy, going to point C, and then it returns back to point A through a combination of entropy loss and temperature increase in radiative substance. Okay. So the way that potential intensity, or the idea that we can use this thermodynamic diagrams to come up with something like a speed limit for hurricane winds works is that you think about thermodynamic subcycles right near the center of the storm. So going in a very small radial inflow leg from a little bit outside the eyewall to at the eyewall, ascending up to some point in the outflow, sinking down a little bit, and then going back down along a moist adiabatic trajectory. And so these thermodynamic subcycles, which I've drawn out here in height radius space, and also in the middle panel in pressure volume space, give a heat input per unit mass of air that's proportional to, have a heat input per unit mass of air that's proportional to the product of the wind speeds and the difference in moist enthalpy between the surface ocean, or the surface, and they're right above the surface. And so the potential work done by this thermodynamic subcycle is given by some efficiency multiplied by the heat input per unit mass of air that's traversing the subcycle. And that efficiency is given by a ratio of the surface temperature at which the air is acquiring heat to the outflow temperature at which it's losing heat out through radiation into space, divided by the surface temperature. Oh, Jonathan?
Yeah, Tim, is there much air that actually moves along C prime to B prime? And if there isn't, does it matter for the theory?
That's a great question. So you can construct the full cycle kind of by thinking about a combination of subcycles that stack up with one another.
Okay.
And so that's the basis for thinking about why this subcycle matters.
Okay.
It's not necessarily clear that you need to have a lot of air that's going back from point C prime to B prime.
Thank you.
Yeah. Yeah, good question. Thanks. So this is the efficiency of a Carnot cycle, and if you multiply this efficiency by the heat input per unit mass of air, and then you think about equating this potential work done per unit mass flowing through this subcycle, which is the efficiency in here, multiplied by the heat input per unit mass of air. And you assume all of this goes into frictional dissipation of winds at the surface, which is given by a product of the drag coefficient and the cube of the wind velocity. And you set these equal to each other. This is where you can get potential intensity from. And so you solve for the wind speed that results from this, and you get an expression for a potential maximum limiting wind speed, which is proportional to the efficiency, the product of the efficiency, the enthalpy disequilibrium, and a ratio of exchange coefficients raised to the 1/2 power. So there's a big work that's been done on body of work that's been done on this by Carrie Emanuel and others, and it's a really nice way to think about how hurricanes work and how they pull heat out of the surface and convert that to azimuthal swirling winds. So, having defined hurricanes kind of in this broad way and gone over the theory that we have for them and how they work in an axisymmetric sense, nothing about this theory that I just presented precludes dry or semi-dry hurricanes. So based on this idea of hurricanes as axisymmetric, warm core convective cyclones which act like heat engines and that generate swirling winds under the influence of rotation, Dry hurricanes would be driven by a temperature jump, or a K naught star minus K that's mostly sensible rather than latent heat. And they'd be driven by sensible heating of inflowing air rather than by evaporation. So that as air flowed in towards the center of the storm, it would be heated up or would decompress at nearly constant temperature through the influence of sensible heat fluxes. And it would require deep troposphere spanning dry convection to work near the core of the cyclone rather than moist convection. So that obviously is not something that typically happens on Earth, because Earth's atmosphere is typically stable to dry convection over very deep layers. But it could possibly happen in other worlds or in idealized settings. And so this is exactly how the cyclone simulated in the Mrowiec et al. Paper works. But I want to dig a little bit beyond that, or go a little bit further. First, by working in a 3D model. Second, by using a closed domain rather than one that's open on the outer walls. So that, and third, by spanning a range of surface conditions rather than just looking at a pure dry-moist contrast. Let's look in between those two and see if there's some kind of continuous transition or not. So in order to do these simulations, I need a simple minimal model setup that allows for hurricanes to form. And that minimal model setup for me starts with radiative-convective equilibrium. So the real Earth has variations in surface temperature, continents, land surface properties, spherical geometry. All of those are kind of unnecessary complications for looking at the work that I'm going to do. So we're going to set up simulations of hurricane worlds by looking at an atmosphere that's in very simple energy balance of radiative-convective equilibrium, where the troposphere has a balance between radiative cooling and convective heating, which can be either moist or dry convection, and where surface evaporation, if there is any, is by precipitation. And in an overlying stratosphere, there's essentially radiative equilibrium with very little convective mixing. So a region that's in radiative-convective equilibrium is like its own little closed world. Dry RCE looks a lot like moist RCE, but the tropospheric heat transport switches from moist convection to dry convection. And so the stratification will also change from being something like a moist adiabat throughout the depth troposphere to a dry adiabat. And so the other ingredient that you need to add to radiative-convective equilibrium to get hurricanes, or to get a world with lots of hurricanes, is just rotation. So that's simple to simulate. You just add in a Coriolis acceleration in the horizontal momentum equations. So this allows areas which have a lot of updrafts and where there's surface air convergence to start to spin up a swirling cyclonic flow at the surface. And those swirling circulations can then self-amplify, because if the stronger winds pull more heat or moisture out of the surface, that allows them to further become focal areas for convection and to develop a stronger circulation in time. So what you end up with is a world filled with hurricanes, or a TC world, or tropical cyclone world. So this is actually a snapshot from a GCM simulation at much coarser resolution than I'm going to use. But this has been found by a lot of different studies. So this brings me to the main research part of the talk, which is going to be about systematically varying the surface moisture availability in simulations and seeing how the formation and maintenance of tropical cyclones respond. So before I get to the model results and a movie or two, I'm going to give a little more detail about my setup. First, we're using the SAM model, System for Atmospheric Modeling, convection-permitting model. It's in a doubly periodic domain. So looking at the A's here on the left-hand side of the plot, if you go out the left-hand side of the box, you would come back in the right-hand side, or if you went out the south side, you would come in the north side. So that's what doubly periodic means. And you'll see cyclones do that in a slide or two. And we're also using constant radiative cooling of 1 Kelvin per day in the troposphere to simplify things, and starting simulations from an equilibrated radiative convective equilibrium state for a non-rotating atmosphere with the surface and atmospheric conditions chosen to match whatever simulation we're doing. So we basically just kind of turn on rotation at some time to an equilibrated simulation and see what happens. And we're using two methods of drying out the surface. The first is to scale the surface saturation vapor pressure by varying a multiplier in the surface saturation vapor pressure between 0 and 1. So the second way we're doing is to just vary the surface temperature between very cold and normal tropical conditions, which essentially spans the dry to moist limit by, as you go to very, very cold conditions, the saturation vapor pressure of water decreases to very, very small values, and it becomes energetically inconsequential for surface heat exchange. So one thing to note is that this beta parameter is actually physically realizable, and we took our notation for it from some literature about surface hydrology over hypersaline bodies of water. So Raoult's law says that the vapor pressure of a substance in an ideal solution is equal to the molar mixing ratio of that substance times the saturation vapor pressure of that pure substance. So salt water, for instance, has a vapor pressure that's lower than that of pure fresh water because some of the molecules near the surface are salt. They're not water. They're not H2O. And so for parts of the Dead Sea, which have a ton of salt in them, beta is actually less than 0.5. So with that, okay, I think I'm going to stop and switch to the movie. Great. Okay. So I'm going to show a movie of the surface wind speed evolution for a simulation with a moist surface on the left and one with a dry surface on the right. So the Coriolis parameter here is set to an elevated value of 3 × 10⁻⁴ inverse seconds to allow multiple storms to fit into the box, and hopefully to allow more than one to fit. And so I'll just play this. So what we see is that storms spin up and organize almost immediately on the right, but it takes quite a bit longer so this is the dry surface on the right. You end up with a lot of storms. And on the left, it takes a bit longer, but then you end up with several storms as well. But they have clearly pretty visibly different properties. So you see the spontaneous genesis in the moist surface case takes a bit longer, but you end up with stronger storms in their cores. And once the storms get going, they really take off. So both the moist and dry storms in this case see significant vortex-vortex interactions, and over time are going to settle into a state with kind of well-behaved storm statistics. So it's fun. This evolves for a while. You can keep watching it. But the main points that I want to get across, and first, this is the only thing you remember from the talk, then fine. But first, that dry hurricanes in 3D happily form and persist in a rotating radiative-convective equilibrium environment. More subtly, these dry hurricanes have big eyes and weaker peak intensities compared to their moist counterparts. And third, it's getting blocked by the play bar at the bottom of this. So I'll go back to my slides. And so third, despite this difference in intensity by about a factor of 2, the moist and dry systems actually end up with similar surface kinetic energy dissipation averaged over the domain. So the broader eyewalls in the dry case compensate for the weaker maximum wind speeds. And so dry hurricanes look pretty different than the normal moist ones in terms of their radial structure and also in their uniformity. So for instance, there are many storms in the dry case. You can see a lot of storms that we've identified here in map views on the left panels. And as mentioned before, they're each weaker, but the azimuthal winds shown kind of at right here look much more similar for the many dry storms in the bottom panel, H here, than they do for the 2 moist storms in the top panel, D. And the structure of the azimuthal wind field is also pretty different. So the dry storms have a broad eyewall, and then a relatively rapid decay down to 0 azimuthal wind as you increase the radius. Whereas the moist storms have a more, features that we're more familiar with, which is that the wind speeds rapidly decay, but then there's a long skirt of a slow decay as you go out further outside the center of the storm. And finally, the structure of the warm core is actually quite different for the moist versus dry cases, which is shown in the blue contour lines in these two center panels. So the warm core in the moist cyclone case is something we're familiar with. It's elevated aloft, but it persists all the way down to the surface. Whereas in the dry case, you see that there's actually just a very small warm core right near the tropopause. And what that is indicative of actually is that we've averaged this in fixed height coordinates. So if you looked at pressure coordinates, like say at 900 hectopascals, you would see a warm core at the center of the storm. But if you have a fixed vertical level of, like, say, right at the surface, or at 100 meters or 500 meters, you don't see a strong warm core. So we also want to understand whether the transition between these two very different structures of vortices is continuous. And that's where some things get interesting and more subtle. So the moist to dry transition is apparently not continuous for genesis. So what we see is that storms gradually transition in size, intensity, and inner structure for a while as you decrease the surface moisture from full moisture availability to something like beta equals 0.7 to beta equals 0.5. What you see is that storms progressively get a bit bigger, their eyewalls get weaker and start to expand a bit. But when you go to something like beta equals 0.1, you just get static, nothing spontaneously forms. And then you go to the dry limit and you see something like the movie that I just showed you, which looks, a lot like an extension or extrapolation of what you would get if you continued along the drying out past this beta equals 0.5 point. So there's some kind of no storms land where storms don't spontaneously form at low but non-zero surface moisture availability. Yeah, Jonathan.
Yeah, Tim, I hope I'm not jumping ahead here a little bit, but I'm wondering what the role of deformation in the environment is. I mean, I've heard engineers refer to deformation space between vortices, and it's certainly getting smaller as you go to the dry limit. I wonder if there's something about the deformation in the flow that just makes things go weird around 0.1.
That's a good question. That's not actually something that we've tried to quantify in a lot of detail. I think that part of the problem there is that the hurricanes, the cyclones, tend to set their own spacing. There is less. There is more deformation between the vortices and the dry limit, but there's also, that's in part because there have just been cyclones that fill up that space. So if you set up a simulation with 4 of them, the way there are for this beta equals 0.5 case, and ran a dry simulation instead, probably others would pop up in between. I think that part of that's an interesting idea. But there's quite a lot of deformation in the regions, even in these white regions between the storms in the moist cases.
Okay, thanks.
So it's not our leader in our kind of current hypotheses for what sets this no storms land, but it's an interesting idea. So we can also look at this by quantifying in a domain average sense what the surface kinetic energy dissipation is. And so that's shown here in the plots at the top and the bottom for both across all the simulations that we did, both varying the surface wetness on the top in this panel A, and varying the surface temperature in the bottom in this panel C. And so the simulations that have tropical cyclogenesis and end up as these T-worlds at some point see an abrupt jump up as you go from very low values of surface kinetic energy dissipation to values that are in the range of a few watts per meter squared. And simulations that don't show spontaneous genesis just stay as flat lines for the whole simulation period. And so we see that this shows us that the no storms land range of parameter space spans from something around 0.3 down to something like 0.01 in terms of moisture space. And it also shows up if we vary the surface temperature, which we thought was really surprising. So as we vary the surface temperature, we see no spontaneous between about 250 and 270 Kelvin. But dry storms form almost immediately at a surface temperature that's very, very cold, 240 Kelvin. So there's a lot of, seems like there's a lot of similarity between these two sets of simulations in the intermediate range of moisture availability, either achieved by limiting the surface saturation vapor pressure with this beta factor, or by limiting it with surface temperature, lead to a similar no storms land. And the final kind of subtle piece of this that I want to get across is that this no storms land seems to only be a barrier to spontaneous genesis, but if you let storms form at one end of this parameter space and then change the surface temperature in time or change the surface moisture in time so that you go through this no storms land range of parameter space, you actually see those storms persisting. So this is showing in the black dots the time average surface kinetic energy dissipation for different surface temperatures ranging from warm to quite cold. And in the bottom, in the range from 250 to 270 Kelvin, you see these black cells that have very low values of kinetic energy dissipation, indicating that they don't develop strong organized circulations like hurricanes. On the other hand, if you start from a very warm temperature, like this red line, and decrease the surface temperature slowly in time, you get formation of tropical cyclones that then persist, and as you go through this forbidden range of genesis for tropical cyclones between about 250 and 270 Kelvin. And similarly, if you start from a very cold surface, shown the blue line, and ramp up the surface temperature in time, you get cyclones persisting through this range of temperature, surface temperature space. And so a final thing to point out about this, to further characterize this moist to dry transition and to provide some evidence that storm properties really do evolve relatively continuously between the moist and dry limits, we looked at this is showing two non-dimensional properties of the individual cyclones. So we compiled these statistics for normalized intensity, which is given by the maximum tangential wind speeds in a azimuthally averaged composite of a cyclone, divided by the potential intensity. We also looked at the inner core vortex regime quantified by the Rossby number, which is given by the maximum azimuthal average speed, Vm, divided by the Coriolis parameter multiplied by the radius at which you reach that maximum wind speed, Rm. And so moist storms, shown in the blue lines up top here, have ratios of maximum to potential intensities that are actually very close to 1. And so they go up over 1 temporarily. And so that's saying that the moist storms reach close to their potential intensities in these idealized TC world simulations. But dry and semi-dry storms, on the other hand, are sitting somewhere between like 0.25 and 0.5. And most of that transition actually happens between about beta equals 0.7 and beta equals 0.5, or beta equals 0.4. And then you have this no storm land of parameter space from 0.3 to 0.01, and you come out the other side for the dry storms at normalized intensities that are very similar to where you kind of left off at beta equals 0.4. Similarly, and in the plot, these plots B, showing the Rossby number of the inner core, or the maximum wind speed divided by the Coriolis parameter times the radius at which you get that wind speed, we see for moist storms a familiar cyclostrophic regime where you have a very high Rossby number, indicating that it's mostly centrifugal accelerations being balanced by pressure gradient forces. But for dry storms and for semi-dry storms, we see a transition to something that's more of a gradient wind balance, where both centrifugal and and Coriolis forces are important to balance the pressure gradient force. And so we see a very similar behavior if we vary the surface wetness. We don't quite get to a surface temperature where you've made the complete transition to dry vortex dynamics, but you see a gradual transition going from storms that reach their potential intensities to ones that are quite a bit below it for 280 Kelvin, and then ones that are below it further still for 240 Kelvin. And also a transition in the Rossby number of the inner core from cyclostrophic towards gradient wind balance to something like gradient wind balance as we cool. So these are kind of the main results of this part of the talk. Again, dry hurricanes readily form in rotating radiative-convective equilibrium. Their properties differ for dry hurricanes relative to their moist counterparts. They have weaker peak winds, larger radius of maximum winds. So again, with weaker peak winds, they don't reach their potential intensities nearly as much. And they also have an inner core vortex regime that's different in terms of its force balance. And the transition appears to be relatively continuous again, except for this kind of weird no storms land barrier to spontaneous genesis, which happens both as we cool off the surface and as we dry it out. And this is, these results are all talked about in a paper by myself and Dan Chavas, who I meant to acknowledge on the first slide. This is the work that I've done in collaboration with Dan Chavas at Purdue. He's been a great person to work with on this. We were both students with Kerry Emanuel in grad school, and it's been fun to see this project through with him. Okay. So that's where the bulk of the new research I wanted to talk about, and there are a lot more questions that spin off from it, but I want to cover one in a small amount of detail here. I think I have time for that. So this exploration started with a fun question because we wanted to try to fit more storms in the domain. And knowing that if we increase F, the rotation rate, that the length scale for storms decreases, we wanted to ask the question, what if we spun it faster? So with that, I'll show a movie of oops, shouldn't give away the result. I'll show a movie of what happens if we crank up the rotation rate to even higher than the values that we've already used. And I'll just switch over. So this should be showing a moist and dry surface. Okay, there it looks like it shows up. With F equals 1 times 10 to the minus 3 inverse seconds, which is very rapid rotation. And we'll see a behavior that's qualitatively different. So the moist surface shows this kind of explosion of storms developing. You see very intense Fujiwara effects because the domain is actually much smaller, and so given wind speeds or interaction speeds, show things swirling around each other much more quickly. The dry system has changed completely in its behavior. And so what we see there is that there's no rapid initial spin-up and then no mature TC world-like final state. The flow appears to just be energetic at the largest scales permitted by the domain size. So it's not closed off into hurricanes, and it looks a lot like 2D turbulence. So the dry case thus appears to be very sensitive to the rotation rate. The moist case might be as well if we pushed it harder. So towards the end of the simulation, from days about 40 to 50, the main vortex is going to break down, and then it's going to do very strange stuff that happens afterwards, with the vortex splitting into two, and then those two finally remerging. So there's going to be this vortex here is going to actually spin off two subvortices in a few days. So there's one, and then there's a second one, which is really wacky. And so those will eventually start to remerge towards the end of this simulation. Though maybe not as I've cropped it here. Yeah. Okay. So stop that and go back to slides. So yeah, the dry system has qualitatively different behavior with a very high rotation rate. The moist system seems to have closed vortices still dominating, but some hints of a different behavior. And so our hypothesis for this is that the dry hurricanes can't form at a convective Rossby number that's too small. So for a dry convective system, the convective or natural Rossby number is given by the buoyancy flux to the 1/2 power multiplied by the Coriolis parameter to the 3/2 and divided by the depth of the layer. And so this, this might look complicated, but it's essentially just a measure of the rotational time scale, which is 1/f, divided by the time scale for convective ascent through the depth of a fluid layer, which is related to the depth of the fluid layer divided by a typical velocity that's achieved by updrafts, and that's governed by the surface buoyancy flux in dry convection. And so in past experiments and simulations of dry convection, people have seen regime transitions with varying convective Rossby number. And so convective Rossby number that's much, much greater than 1 is the typical case for Earth-like atmospheric convection, which is where convective ascent through the troposphere happens much more quickly than planetary rotation. On the other hand, a Rossby number, convective Rossby number less than 1 indicates that plume ascending through the troposphere would make that ascent on a time scale comparable to planetary rotation. And so we can attain that limit in these simulations, and that actually happens in deep ocean convection too, which is why John Marshall is on some papers that talk about this, which is that sinking plumes of ocean water are much slower than atmospheric convection, and that happens on time scales comparable to planetary rotation. So as we look at dry rotating radiative convective equilibrium across the range of rotation rates, what we see seems to be consistent with this hypothesis. So at the top right of each of these subpanels is shown the approximate convective Rossby number for a simulation with varying Coriolis parameters. So increasing the Coriolis parameter as you go from top left to top middle to top right to bottom left to bottom middle to bottom right. You see that the convective Rossby number decreases as you increase the Coriolis parameter, and you also see the breakdown of a dry TC world, which is very neat and tiled, into something that's more chaotic, turbulent, and ultimately doesn't contain closed organized vortices at all. So a natural next question for this, which we haven't gotten to looking at, is whether moist storms also break down and whether we can formalize this scaling. If moist storms don't break down, why does moisture keep them from being susceptible to the same rotational constraints? And I think I will, I can mention this briefly. To finish off, I just want to talk about a few interesting other aspects of simulations that we just did to set up the rotating cases. So these are like initialization simulations that are non-rotating and show a span of moist to dry radiative convective equilibrium results. So a few interesting things. First, there are these sharp temperature inversions at the tropopause that develop where you have a deep overshooting layer, similar to what was found by Olivier Pauly and Isaac Held in some work, but this shows up at a certain surface dryness, and we don't understand why or what controls how strong this inversion is. We'd like to understand that better. Second, and surprisingly, the cloud fraction shown in the middle panel actually increases as you decrease the surface moisture, which seemed surprising and strange. It might be explainable in terms of the weaker asymmetry between up and downward motions for dry convection, or in terms of a change in static stability near the upper tropospheric cloud peak, or maybe something else. And finally, shown on the right, as the surface moisture availability is reduced at moderately low beta values, you end up with these interesting Virgo worlds where there's very low, where you have a precipitation flux, say for this beta equals 0.1 case, that's millimeters per day around 850 hectopascals, but then it drops to very low values at the surface. So this is indicating that most of the precipitation falling at 850 is evaporating before it reaches the surface, and you have this very vigorous internal atmospheric water recycling with a trickle of evaporation and a trickle of precipitation, which I think is fascinating and looks a lot like in some ways like what parts of the Intermountain West U.S. look like in summer, when you can see a lot of virga rain falling from clouds, but it's so dry that very little of it reaches the surface. So to just kind of summarize, bring me my conclusions. Again, the main take-home point of this talk, again, that dry hurricanes readily and rapidly form in dry rotating radiative-convective equilibrium. Two related points: in the moist to dry transition is not continuous in terms of spontaneous genesis, but it does across the whole range of boundary conditions. We do see supporting of cyclones once they form, and that semi-dry storms look like fully dry ones in non-dimensional space, with lower potential intensities lower maximum intensities relative to the potential, and also lower Rossby numbers in the core of the storm. And then finally, for the sensitivity to rotation rate, we see a transition in global flow near convective Rossby numbers of about 1 for dry storms, but not for moist ones. We're not sure why at the moment. So taking a step back, most idealized modeling work has really focused on kind of realistic tropical cyclones. So if we think about 3 dimensions of parameter space, there's more than just this, of sea surface temperature, of surface wetness, and of rotation rate. You know, most work has been done in a range of that range of parameter space near rotation rate of subtropical values, which is realistic, 5 times 10 to the minus 5 inverse seconds. Around a surface wetness of 1, like ocean water, and around 300 Kelvin for a surface temperature. So the results that I've shown today kind of fall along this green line, parameter space that I've sparsely sampled in this work, where we crank down the surface wetness, or we change the sea surface temperature to compensate, and we're working at relatively higher rotation rate. So I could have a line going out this way as well. You know, other work by Carey from years ago suggested that there's possibility of hypercanes if you go to very high sea surface temperatures. But to close, I think there's a whole lot of parameter space to explore and room to push the boundaries of what we do in idealized simulation of hurricanes, and that there's numerous signs that there's quite interesting territory in many directions, and perhaps we can learn a lot from pushing outwards. So that closes things for me. Thanks for your time.
Thank you, Tim. So we're going to open up the floor to students to ask questions first before we open up the floor more generally. And I'm happy to read questions if you put them in the chat. So yeah, any student questions for Tim? Okay. I guess I'll open up for questions more generally. And I will start things off and ask or no. Oh, John has a question, but I'll start things off and ask why there were. Oh, go ahead, John.
Go ahead, Larissa. No, you go ahead, Larissa. I didn't mean to interrupt you with that little bell. You go first.
I was wondering about the rotating or non-rotating radiative-convective equilibrium and why there weren't any low clouds in your simulations.
So that's a good question. I'll go back to that slide briefly. Trying to go back.
We're not seeing your screen share right now.
That should come up. Yeah, there we go. See, is that up now? Yeah. So the cloud fraction scale here goes up to 1, and so it's this is indicating that the dry cases have a ton of high clouds. The moist cases have a little bit of low cloudiness, which is typical of what you see in RCE. There's not, there's maybe 5% low cloud fraction. Once you get to moderate, kind of moderately low surface wetness, the low clouds have actually shifted upwards to be around like the LCL. And so around beta equals 0.1, your low clouds are actually, at 850, 700, or sorry, 750 hectopascals. And that peak is a little bit larger. It's maybe like 10% low cloud fraction. But I think overall in RC, most studies don't find a very large low cloud fraction. Most low clouds in the kind of real tropics are confined by trade inversions, features that we don't see in simulations of RC. Does that maybe make things clearer?
Thank you. Yeah, thank you. I was going to show the video. Yeah, thank you. We have a question from Karen. A question from Karen. Any explanations for the gap in the temperature range where the dry storms don't form?
Yeah, so it's a great question. We thought about that a lot. And the one thing in common, my supplemental slides. This was kind of an attempt at a non-dimensional plot of where the no storms land is. It seems like when the ratio of evaporation to the surface heat fluxes is relatively low, either obtained by varying the surface temperature or varying the surface wetness, shown in the circles here for surface wetness, or the squares for surface temperature, that you end up with kind of this no storms land case. So this suggested to us that there's maybe something about this ratio of how much surface flux is evaporation to the total that could matter, and a way that could matter, and it's not completely clear to us how this would work out exactly, is through this linkage here for dependence of precipitation flux on, or the way these precipitation flux profiles look, I should say. So the idea would be that rain evaporation, if you have only 50% of your surface heat flux being carried by latent relative to sensible heat flux, that you might develop a relatively deeper dry boundary layer and see more rain evaporation if you start to develop a vortex, and that would make it harder to develop a spin up a vortex from nothing. So kind of long-winded way of saying, as you decrease the surface wetness or the surface temperature, you possibly get into a regime where you have a lower precipitation efficiency, but still one that's where still an equilibrium that's precipitating, and that might be susceptible to, as you start to develop a storm, having downdrafts cut off the low pressure center at the developing storm. Thanks for the question, Karen.
Thank you. I think John Martin had a question.
Yeah, and I'm glad you guys went first because mine's really out there. But Tim, I wanted to say one thing that's an unfortunate casualty of this COVID-19, among many others, is you don't get a round of applause that you deserve for an excellent talk. That was really great. Thanks so much.
Thanks, Jonathan.
I wonder if you could comment on the implications of the presence or absence of these convective type entities at high latitudes. Because one of the interesting things about Arctic cyclones is that they tend to be larger in radius and last longer than their mid-latitude counterparts. And as I'm listening to your presentation, I'm thinking maybe there's just an extra added vortex punch at high latitude to baroclinic developments because there's a presence constantly of some of these convective elements. Do you think that's crazy?
So it's a good question, Jonathan. I think that really depends where in high latitudes you are, because over the Arctic sea ice in winter, you're not going to see any convective destabilization of the atmosphere. It's likely very stable. So you might have explanations there for enlargement of cyclones. Actually, if the deformation radius gets larger because the static stability goes up, for instance.
Yeah. Okay.
But over kind of subpolar oceans that are open water in winter, for sure, those are really susceptible to pretty deep convection, and it's an environment where we don't always think about convection as being important. But if you move move Arctic air over water that's just just a little bit above freezing, it's a huge temperature jump, and you can very easily trigger pretty intense convection.
Yeah, and when I was first a graduate student, people were talking about polar lows in a fairly serious way, and it was a hot topic, and there was a question about whether they're extratropical or whether they're ASE interaction. And it sounds like to me you've made a convincing case that those small scale disturbances are almost certainly ASE interaction storms of the nature of tropical cyclones.
I mean, so I think that certainly could be the case. I'm not sure if I've convincingly proved it with this talk, but I think that you can certainly make the argument that you can get convectively coupled rotating systems without a huge influence for latent heat release if you've just got that surface temperature jump.
Thanks.
I see a question in the chat from Alicia and Nuo. It's interesting that both dry and moist cases don't have eyewall replacement cycles in simulations. Does that suggest the formulation of ERC is not a function of moisture parameter? That's a good question. I don't, I gave some of this to a grad student of Kerry's to look at for looking at eyewall replacement cycles, and there's some, the moist cases really don't have very much at all. The dry and semi-dry are a little more ambiguous, but they don't show the classic kind of annular eyewall replacement cycles. They just have eyewalls that are a little more, a little less symmetric and constrained overall. I don't know whether that indicates decisively that eyewall replacement's not a function of moisture. None of these simulations have kind of mean shear in them either, and they don't have radiation interactions. So either of those things could be important as far as I'm aware for eyewall replacement cycles. But yeah, it's an interesting point and good observation. Thanks.
Okay. Maybe we can all thank him in the chat since we can't applaud. I don't see any more questions.
Yeah, and I guess just if I should say, Larissa, if anyone's interested in meeting with me later this week, I have a few meetings tomorrow, but could make time to talk about this if anyone is interested. Or about anyone else's work, I would be happy to extend the virtual visit to whatever time is needed. Thanks, and thanks, Larissa.
Thank you, Tim. Oh, I see all the virtual applause. This is great.
Yeah, great. Love it.